Okay, so in the last class we discussed about like hybridization and how the different molecules, like covalent molecules basically, so all these hybridization techniques are related to covalent molecules and how covalent molecules can form like these different shapes based on their hybridization, and how we can actually predict the hybridization and then the shape, things like that. So if you guys have like doubts, then so the problem sets now do not have that, right? But I will send out like a big PDF which has like many questions to practice. So there are like different chapters in them. So there's a periodic properties, atomic. So that is basically my question bank for all the things. But I think that I'll just share it with you all, so that there will be like tens of thousands of questions in there. But it is like chapter wise. So you can just go to the chemical bonding chapter and like solve these questions, and the answers will be there. So you can check your answers and do that. I'm not including that in the problem set, because you guys are like smart enough to know what's good for you. It's not everything has to be a problem set, and that's the idea behind having a more challenging problem set in the class. Okay, so that will be given. Practice that. Ask me questions about hybridization, things like that, how covalent molecules form bonds. Okay, now if we think about the covalent molecules are like, they can form like a separate entity, right? So you can have, if you have a methane molecule, the methane molecule can be separate. You can see that methane molecule that doesn't have to be associated with other methane molecules necessarily. Okay, they have their own identity. So you can have like a covalent molecule. But things are not very similar for ionic compounds. We saw that earlier, because when you have ionic bonds, and the electronegativity difference is very high. So things form ionic bonds, and it's not just the complete transfer of ions. It is more complicated than that, because when you transfer the ions, you form a cation and an anion, but you do not form like one entity of like, you will never have one NaCl just hanging around. It's not possible, right? So NaCl, when it forms, it will be possible, but in like vapor state. So for now, for like ionic compounds, let's think about like ionic compounds will form a lattice. Like they will only be, it's like stacking boxes. So like if one box is NaCl, you need all the other boxes stacked on top of it, on its side, below, and everywhere, so that it can form like a stable phase, like a stable entity. Okay, so that thing is like an ionic bond. So in ionic compounds, they form ionic crystals in the crystal lattice. Some of you might have like done this in like solid state, things like that. But let's start today by thinking about ionic bonds and how these form ionic crystals. So these ionic crystals are forming a closed pack. Why do you think like an ionic, so assume that these ions, first, the ions are like billiard balls. Okay, this is like an assumption. Let's assume that. And then there will be, in that entire lattice, it will be charged neutral. That entire lattice somehow will not be charged. So this will be charge neutral. Okay? Now these billiard balls are like different sizes. Like some of these are small, some of these are big. Which of these is a cation and which of these is an anion? More likely to be a cation and which is more likely to be an anion? Like a smaller billiard ball or the bigger one? Remember Z star, which was Z by E. This was the effective atomic number. This is the effective atomic number. And this basically give you an idea about the size, right? So the bigger this is, the smaller the size gets. So this, like the size is like inversely proportional. Does this make sense? This part? The size is inversely proportional to the effective nuclear charge. When the effective nuclear charge, effective atomic number, effective nuclear. This thing, when it increases, this forms a smaller, and when this is less than 1, this forms a bigger. So which of these two billiard balls is more likely to be a cation, and which is more likely to be an anion? Think through an example. And take an isoelectronic species. So let's suppose take an Na plus and an F minus. Think about that. So what's the Z star for Na plus?
11.
It's easy, right? But what is it? So what is the Z for sodium? 11. So what's the Z star for Na plus?
11 divided by 10.
Yeah. Yep. Z star for sodium is 1.1 because the atomic number for sodium is 11 and the number of electrons in sodium plus is 10. So Z star is 1.1. How about F minus? Come on.
Wait, why is it 1.1?
Because it's 11 over 10.
Oh, okay.
0.9. So which is larger? Inversely. So which is larger?
Sodium?
Why? Because I just said it is, when this is large, the size is small. This is what inversely proportional means, right? So when you have something that has more Z star will have a smaller size. So this one has more Z star, so this will have a smaller size. So cations are smaller. And anions will be larger, generally speaking. Okay, they are comparative. So if they're Z, like the Z values are, if they're isoelectronic, if you think about that. Okay, so which do you think will surround which one? Like the smaller will be surrounded by the larger ones, or the larger will be surrounded by the smaller ones? When you think about it. So if you are trying to close pack something, okay? So say you have three anions, okay? So these are all negatives. The cations are likely to sit here, right? Because if you want that thing to be like as close as possible. So, there will be this kind of a structure in which the cations are filling in the voids of anions. So the anions are like the bigger ones, and the cations will be like sitting inside of them because of their smaller size, because they can actually fit in that smaller space. So basically the lattice will be formed by these anions, and the insides will be the cations. Now, if this thing is a little bit bigger, so if this cation becomes a little bit smaller, what is going to happen? Will the closed pack thing be maintained in that case? If this just becomes a little bit smaller, so what will happen? It will like bounce around. It will not be like tightly packed inside these three, right? So there is a particular number or like a range of numbers in which you can, so mathematically, so this becomes like a mathematics problem. So you have three big radiuses, R, and R. What is the radius of the smaller one? So this becomes a mathematical problem in which you are trying to find out this smaller, so this smaller one is say small r, and this bigger one is say capital R, whatever. So this is like the radius of the cation, radius of the anion. So if I'm asking you what's the ratio between the ratios of the cation and the anion, so this becomes a mathematical problem. Okay, so this is what I want you guys to like think about. There are particular ratios in which this can be tightly sitting, because if the cation becomes smaller, the RC versus RA becomes smaller, and if the cation becomes smaller, this does this rattling thing inside of it. It is not like tightly. The other way is if it becomes a little bit bigger, then it also does, so maybe it becomes a lot bigger than all these, then do you think like having a triangular setting will fit the cation, tightly packed, closed pack? First of all, why do you need this closed packing? Why not let it rattle inside? Why not? Why do you have to have a closed pack? What happens when you are closed?
Unstable.
Sorry?
If it would become unstable, I'm assuming.
Yeah, when it is like not closed pack, it becomes unstable. So closed packing gives you stability. But how? Or why? Because the closed pack is between a positive and a negative. What happens between a positive and a negative? They attract. I'm not talking about like the charge. The charges are cancelling out, yes. But the nature of this cation and anion is such that they will attract. And attraction does what? Stabilizes or destabilizes? Attraction stabilizes, okay? So when you have more attraction, there will be more stability. And what is that attraction force? It is some constant Q1, Q2, the charges, over R square. And R is the distance between them. So if the distance is smaller, then you have more stability. And that is why you need to get it as close as possible. Right? As close as physically possible. You have to get them close. That is the logic behind a closed packing. To get the least amount of energy, that means it is going to be like the most stable one. Okay? The idea of closed packing is clear, like why we need closed packing. Okay. Now, if this is like really small, like less than, so this arrangement is only true for a certain radius ratio for cation to anion. If that radius is smaller than this particular thing is not going to have be stabilized. So then what we are going to have, it has to be something like this in order to stabilize it, because then at least it has two anions like touching the sphere, the cations. Okay, so what's the shape in here? of the lattice, like of the lattice structure. What's that shape? It's a linear, right? So the radius ratio is more, so the radius ratio is always cation over anion, okay? So when is the radius ratio more here or here? Where is the cation smaller? In the linear or in the trigonal? So if it is smaller, so if it is, this thing has a void in between, so these three cationic billiard balls are making this void in between. If the ball fits, if the cationic billiard ball fits perfectly well, it's fine. But if it's small, it goes over there. And if it's big, then what will happen? Like then, either you'll have to get more, like it's not a case of either, you need to get more anions to surround it because the cation was first smaller. So like even 2 will be able to do that. It becomes a little bit bigger. So now you need 3 to surround it. Now it becomes more bigger. So you need more anions to surround it to make it stable. If it becomes more, you need more. So basically, the RC by is increasing this way. Okay. So what is the coordination number? Coordination number is just the number of anions that needs to surround it. So it's 2 in here. What about this? 3. The shape is linear. The shape here is trigonal planar. Yeah. When you have more, what do you need? You need more anions to surround it. So what will be the shape? 4. It will be 4, yes. So it will be, the coordination number becomes 4. What shape did we have in the bonding, when we were thinking about hybridization? Yeah. Yeah. It's a tetrahedral.
What was CN? Coordination number?
Yes, sorry. This is coordination number. So it is just the number of anions that are surrounding the cations. Yeah. Is this making sense or? Okay. It might not be because I'm like not up to my game today. So let me know. I can go in more detail or whatever. So this becomes a tetrahedral. It becomes a 4. So that tetrahedral shape. Now, this can also form a square planar shape. Now, covalent bonds can also form a square planar in certain cases. So in sp3 hybridization, we saw that there were 4 orbitals involved. sp3 gave tetrahedral, but there is a special configuration in covalent bond, nothing to do with this. There is a dsp2 configuration. It's a special kind. So not sp3, but dsp2 configuration in which you form a square planar. So when you have a coordination number of 4, you can either form tetrahedral, or even in this case, a square planar. Which one of these do you think is more common? Tetrahedral or square planar? Tetrahedral will be more common because that's generally more the simpler way of like nature that it exists. DSP2 or like the square planar thing, which are different by the way, they can have like a square planar, but this is more common. So when you have like silica, that forms like a tetrahedral. So all these oxygens will form the apexes of the tetrahedron. And where does the silica go? So what was tetrahedral shape?
It was like a pyramid, but
Yeah, with a stick on top. So it's like a pyramid, something like this, with a stick on top. Okay? If there is oxygen here, where is the silica? Silicon. Yeah, here. And you will see this kind of, this shape many a times in geochemistry, mineralogy. We'll use this shape to represent, because oxygen is the most abundant element in Earth's crust. That's the most. What's the most abundant element in the entire Earth? What is the core made of? Like the entire core. What's the bulk thing that exists in the core? Iron. So when you talk about bulk Earth, like entirety, then iron is the most abundant metal. And why do you think iron is the most abundant element? We have not dealt with this, but I just wanted to take you guys, like, I want you guys to take a guess. Why is iron most common? What is the answer to everything?
Energy.
Yeah. Come on, tell me. Say the word. Why is iron the most abundant? Why do you think it is?
it has something to do with stability.
It's most stable. What is most stable? The iron nucleus is the most stable nucleus. Out of all the elements in the periodic table, we'll see that when we'll be studying about, if we get the time to study about nucleosynthesis and how elements are forming. So during the Big Bang, certain elements form. So hydrogen, helium, within the first few minutes, these first few seconds, milliseconds, or whatever, like things started to form, right? And then you had like big stars in which fusion was happening. So hydrogen and hydrogen come together to produce helium, like the different isotopes. Helium and helium come together helium and hydrogen come together to form, say, something like lithium. Now lithium is really, so there are certain isotopes of lithium which are really, really rare. They can only have formed during, you don't have to write about this thing, just, it's a fact that I'm like just trying to share with you, because it's important. Because if you have lithium-7 or like, if there are certain isotopes, I forget the exact isotopes, but there are certain isotopes of like aluminium, lithium, that could have only formed during the first few, 1,000 or some years of the solar system formation, during that Big Bang nucleosynthesis. Okay, so if you have something like that old, that means it was formed very close to the Big Bang. Now there is other kind of nucleosynthesis which is called a stellar nucleosynthesis. The stellar nucleosynthesis is what is happening, say, like in our stars. So that our star is basically doing fusion reactions. So there is a hydrogen-hydrogen fusion that is generating some helium, some lithium, all these kinds. And then as the size of the star becomes bigger and bigger, more things starts to fuse with each other, because a bigger star will have more energy, more temperature, and at those higher temperature, more and more things starts to fuse with each other. So there will be like giant stars in which carbon can be forming, oxygen can be forming, nitrogen can be forming, all these things form in stars. So every element in that we are made up of in your body has been made in some star, every element. So like basically when people say like you're stardust, you are, I mean actually. So like every element that you are made up of is basically originated in some star at some point.
Does that make the stars, like the more things fuse with it, does it make it more unstable? Or
The entropy increases. Now we'll talk about that. So everything, so the universe, to simplify your question, I mean, yeah, if there was, but the thing is, these are all nuclear processes. So the nuclear processes doesn't necessarily go hand in hand with the laws of like general chemistry. So sometimes these things, when you fuse these things together, there's a huge energy that is released. So E is equal to mc square, things like that. So when two atoms fuse together, the final product will weigh less than the sum of the initial reactants. And that difference in energy is what got released, right?